So chapter 3 is where we'll now begin exploring some geometric ideas, beginning with vectors in Euclidean space. Now once we get started, it may seem like we're beginning with a brand new subject, but in fact the further along we get, the more apparent it's going to be that these ideas are nothing but an extension of what we've already been studying. So we're going to begin with the idea of a geometric vector. So geometric vectors can live in either two-dimensional space, that's what this R2 means, or they can live in three-dimensional space, and that's what R3 means. So that's what we're going to define now. So a geometric vector has really two attributes that entirely characterize it, where it begins and where it ends. And really the vector itself can be thought of as the journey between an initial point and a terminal point. So that's how we'll say this. A geometric vector in R2 or R3 is an arrow which begins at an initial point and ends at a terminal point. So that's how we'll define a geometric vector. And there's a notation that you can use to write these down efficiently. And really, if there's only two attributes, an initial point and a terminal point, that's all you should really need to include in your notation. And also include something to make it clear that you're talking about a geometric vector. So here's the notation. If I want to talk about the vector that has P as its initial point and Q as its terminal point, well, then I'll just write P, Q. And really just to emphasize that P is the starting point and that Q is the ending point, terminal point, I'll just write an arrow on the top like this. So it points from left to right, indicating that the left point here is where the vector starts, and the point Q on the right, that's where the vector ends. Now I could flip that around. I could say PQ, or I could write it as QP, but then I would just draw the arrow in the other direction. So this second notation is a little bit less common, but some people do use this quite a bit. I will make use of it occasionally, but most of the time, whenever possible, I'll use this notation because I feel like it's just one little bit easier to read than the one on the right. So why not keep it as clear as possible? But there are certain circumstances where it's useful to have access to this notation as well. Okay, let's draw a picture of what this might look like. So remember what I said. I mentioned they could live in R2 or R3, and up until this point, the distinction hasn't been made clear, but in this picture it will. We'll do an example of each. So let's draw an example of a vector in R2. So R2 is just the Cartesian plane. You've got your x-axis and you've got your y-axis, right? And maybe we've got a point here, which I'll draw as the point P, and then we've got another point over here, which I'll draw as the point Q. And then the vector is actually the arrow between them, which I'll just draw in green so it stands out. So you can see that I'm drawing exactly this vector, right? It starts at the point P and then it goes all the way to the point Q, and then the arrow at the end really just makes it so that you can, because you might not have seen me draw it, you might be looking at the picture after the fact. Well, the arrow is there just to indicate which is the terminal point. So the vectors point to their terminal points in that sense. So this is a vector PQ, and this is in R2 because it's in two-dimensional space. And I mentioned we can also draw vectors in three-dimensional space. Now how are you going to draw three-dimensional space? Well, it's a little bit more involved, right? You're not just going to have an x-axis and a y-axis. We're going to have three axes. We're actually going to introduce a new axis called the z-axis. But there's still a very particular way that you'll draw three-dimensional space so if you want to follow the standard, which you most certainly do. And this is how you're going to start it. So you start off drawing the x-axis as you normally would. Now normally if I was just drawing two-dimensional space, I would draw a vertical axis now and call it the y-axis. But I want you to imagine that now flat coming forward instead. Imagine if I just took this Cartesian plane and I just flipped it forward. So it was flat on the table, kind of coming out towards you. Then you'd see a y-axis coming out like this. Now, for the vertical axis, this is where we'll draw the z-axis. Okay, so that is three-dimensional space. And the point at which all three of those axes intersect is going to be called, as usual, it'll be referred to as the origin. And that's actually true over here as well. The point where these two axes intersect, that's called the origin. So no matter what dimensional space you're in, O is always the origin, and it's where all your axes intersect. Okay, so sometimes I label the Cartesian, like if you just forget about the point P and Q and the vector, just look at the XY plane, sometimes I'll label them as R squared to represent the Cartesian plane. And if I want to follow the same convention, I would label this with R cubed. Just say that I'm talking about three-dimensional Euclidean space, the XYZ space now. Okay, so drawing things is a little bit trickier, and if you're not careful, you can make a mess really quickly. And I'm guilty of doing that quite often, so I'm going to try to do this very carefully. But before I draw anything, I want to make one more point. Notice that if I were to forget about the y-axis, what I really have is essentially R2. I have an x-axis and a z-axis. It's just like the xy plane, but where the y-axis has been labeled with a z instead. So if I take out the y-axis, I really just have the Cartesian plane again. Or it's a copy of the Cartesian plane, but we'll refer to it as the xz plane. So it's what you would get if you totally threw away the y-axis. Now, similarly, I could throw away the x-axis, and what I would have is a copy of the Cartesian plane, just oriented differently. One of the axes is coming out towards us, and the other one's going straight up. So that's the yz plane. And then lastly, if I wanted to get rid of the z-axis, I would have the xy plane, which is really just the Cartesian plane, but just flattened instead of written vertically. Okay, so what's the point of this? Well, when you sketch a point in R3, let's start with a point like this. I'll draw a point P, and I've certainly drawn a point. I've given it a name. Now, where is that point exactly? It's not really easy to see, right? For example, if I look over in this picture, I can see that for both of these points P and Q, the x and y coordinates are positive. But if I had taken this point P and drawn it over here, then it would have had a positive y coordinate, but a negative x coordinate. If I were to take this point Q and pull it down below the x-axis, where I'm pointing my pen now, well, then it would have a positive x coordinate, but a negative y coordinate. Well, what about this one? Is the y coordinate of this point positive or negative? It's really difficult to tell, right? Without a little bit more context. So that's why why is it so hard to tell? Well, because you're trying to draw a three-dimensional idea on a two-dimensional piece of paper. So it's not going to be perfect, but there are ways you can help to make it a little bit more clear. So I'll draw something which is called a projection. You can think of this as a shadow. If the sun were up where my pen point is, and it was looking straight down, the sun were shining straight down this point where a big thick black dot, like the size of a raisin or something, it would have a shadow down directly below it, right? And that shadow, this point has a shadow in the xy plane. But it also has a shadow in the xz plane. If the sun were right along the y-axis, shooting straight at it, it would leave a shadow on the xz plane. So I can draw a shadow there. And then if I had the sun looking at the point this way, along the x-axis, it would cast a shadow of this point P in the yz plane. So, and maybe it's going to look something like this. And by drawing those, you can kind of get a little bit better of an idea of where this point is. It's really supposed to be coming out forward a bit off the page, but not too far, but a little bit off the page, rather than being behind the xz plane, so to speak. It's in front of the xz plane. So that's just good to keep in mind when you're drawing points in R3. It can get a little bit tricky to make them clear, but you do your best, right? And I'll be the first to confess I'm not particularly good at this, but I do my best. So we have enough now to draw an example of a vector in R3. So I'm going to draw. Remember, we have this origin. There's no reason we can't take the origin to be the initial point, or even the terminal point. You could have the origin be either your initial or terminal point. And in this example, we're going to take it to be the initial point, and the point P is going to be our terminal point. So that's an example of a vector in R3. So this is a vector, and I'm going to write OP because O is the initial point and P was the terminal point. And that's a vector in R3. Okay, so why did I choose to use the origin as the initial point in this second picture? Well, just because if I drew another point, I would have had to draw 3 shadows to really make it clear where that other point is, and the drawing, you try it, you'll see that the drawing can really quickly become hard to read. So I just wanted to keep this picture as simple as possible, so that's why I took advantage of the fact that we already had one point, namely the origin on our graph, so I used that as the initial point. Okay, so that's just an example of each and a picture of each. So you can have geometric vectors can only take place in 2-dimensional space or 3-dimensional space. They're spatial objects. And I want to add afterwards. Let's read this note. We do not distinguish between vectors which have the same length and direction. If any of you have taken a course in physics, maybe in grade 10, 11, or 12, and if you haven't, don't worry about it. I'm still going to go through this from scratch, but if you have taken a course in physics, it will help to think back to that as a comparison. When you first talked about the difference between vectors and scalars, you probably would have introduced the vectors as objects that have not only a magnitude, but also a direction. And in fact, vectors are entirely characterized by their magnitude and direction. So how is that going to play into geometric vectors in R2 and R3? Well, we're just not going. If two vectors have different initial and terminal points, but their lengths, as in the length, as in if you measure the length of the arrow as a line segment, and their directions, in other words, their orientations, the direction that they point, are the same, even though their initial and terminal points are different, well, then we still take those vectors to be the same. We don't. That's what it means to not distinguish between them. So that's what this note is saying. So we do not distinguish between vectors if they have the same length and direction. So what would that maybe look like? Let's look at an example. So I've drawn an axis in advance here just to make the end result look a little bit cleaner and a little bit more to scale, because I didn't trust myself to draw it freehand. But let's write down some points here. So, but this, you can see we've got a copy of the Cartesian plane. So consider the points A, B, C, and D as follows. So, because we're going to draw 2 vectors, we need an initial point and a terminal point for each of them. So let's take A to be the point 0, 1, and B to be the point 3, 5. And then we'll say C is going to be the point -2, 1, and D is going to be the point 1 and 5. And it's going to turn out that really the axes that I've drawn have exactly it's drawn exactly the right size to draw these 2 points comfortably without having a bunch of extra space. And that's just because I knew what the question was in advance and I drew this already. But that in general, you might want to draw this XY plane with a scale, in other words, where you decided to draw the lines. Let's take each of these notches to just represent 1 unit along each axis. But you might want to choose your scale based on the range of X values and Y values of the points that you have. But in any event, I had the advantage of having that drawn in advance this time. So let's plot these points for starters. A, 0, 1, well, that's this point here, right? Has an X coordinate of 0 and a Y coordinate of 1. So that's the point A. The point B has an X coordinate of 3 and a Y coordinate of 5. So the X coordinate is 3 here, Y coordinate 1, 2, 3, 4, 5, and that'll put us up here. In general, it's not a bad idea to actually label these as 1, 2, 3 along the x-axis, but I just want to, I'm not skipping that step because I'm lazy. I'm skipping it because I want to just keep this picture as minimal as possible. The less things I draw on the axes, the less things that will be there to interfere with the picture that I'm trying to draw. So this will be the point B, and then the vector that goes from A to B, if I draw it in green, will look like this. So that would be the vector. If I write down the notation for that green vector, that would be this. I'd have AB, and then which way should I draw the arrow? Is the arrow going to point to the right or to the left? Well, if you refer to the notation up here, if you have a vector with initial point P and terminal point Q, you want the arrowhead pointing towards the terminal point Q, right? Or if you use this notation, if I wrote BA, I'd want the arrow pointing to the left. But since I wrote it with the initial point first, down here. A is the initial point. I want the arrow to go like this. Okay, so what else can we do? Well, what about these other 2 points? This point C, let's plot this point, -2 and 1. So the x-coordinate is -2 and the y-coordinate is 1. And then this other point, I'll label that actually before I forget, C. And then the point D, 1, 5. So x-coordinate of 1, y-coordinate of 1, 2, 3, 4, 5. So we've got this point here, and that's going to be the point D. Now if I draw the vector that has initial point C and terminal point D, well then I get the vector CD. Okay, and really the purpose of this example is to give you, well, this is, if you look at this, really what is the vector CD? Really, the point C is just the same as the point A, but it's been shifted 2 units to the left. The point D is actually just exactly the point B, but it's been shifted 2 units to the left. So the vector CD is nothing but the vector AB, just shifted 2 units to the left. So because they have the same length and direction, we don't distinguish between them. They're equal. So we can say this. We'll just say AB is equal to CD because they have the same length and direction. Okay, so that's really all there is to this remark. That's all this is saying. So if you just take a vector and it's already drawn with an initial point and a terminal point, and you just slide the vector in any direction without actually stretching it or bending it or pulling it in any, no twisting or anything like that, just a nice smooth translation. So if I've got a vector like this, and you can think of a pen as an example, right? It's the same pen no matter where I put it. But if I rotate it or change the orientation, well then it's a different vector. But if all I do is just slide it to the left or the right or up or down, it doesn't change the vector. Okay, so with that in mind, if the actual initial and terminal points don't matter so much as the magnitude and direction, if magnitude and direction are the only thing that matter, then there's actually only a single vector which has the same initial and terminal point. And that's called the zero vector. So that's what we're actually going to define here and actually give a notation for it. So the vector whose initial and terminal points coincide, in other words, they're the same point, is called the zero vector. So it's the vector with no magnitude at all. Or actually, I shouldn't say no magnitude, but a magnitude of 0. Every vector has a magnitude, but there's one vector who has a magnitude of 0, and that's called the zero vector. So we will write that down here, and it's denoted by 0, and then with this little half arrow on top, which is called a vector arrow. And we've seen this notation used in the past. In particular, used as a column matrix consisting entirely of zeros. So in some sense, you might think, well, that's an abusive notation if we're using the same notation to mean different things. But what turns out to be the case is that these two objects, the vector whose initial and terminal points coincide, or in other words, the zero vector, and a column matrix consisting entirely of zeros, they really aren't different at all. So that's what we'll see as we move forward. So it's no coincidence that the notation is the same. So that's the zero vector.